Freight trains stretch across the American landscape every day, rolling through cities, farmland, deserts, and mountain passes with a presence that feels almost unreal. A single locomotive at the front can haul thousands of tons of cargo across hundreds of miles without hesitation, dragging steel, coal, grain, and shipping containers as if gravity had somehow loosened its grip. At first glance, the math feels wrong. A locomotive weighing about 368,000 pounds pulls a freight consist that can exceed 10,000 tons, which translates to roughly 20 million pounds trailing behind it. That means the engine at the front is hauling around 50 times its own weight. In other forms of transportation, that ratio would end in spinning tires and mechanical failure. A semi-truck could never attempt such a feat on asphalt because the friction between rubber and road would overwhelm it immediately. The truck would strain, its wheels would lose grip, and the load would stay planted. Railroads operate under a completely different set of physical conditions, and that difference begins at a point smaller than most people ever notice. The entire system rests on a contact patch between wheel and rail that is shockingly small. Each steel wheel touches the steel rail over an area roughly the size of a dime, and on worn wheels that area can shrink closer to the size of a nickel. That tiny circle of contact supports tens of thousands of pounds. Steel pressing against steel may sound slippery, and in fact it is, which turns out to be an advantage. Engineers describe this interaction through a coefficient of friction, and for steel wheels on steel rails under normal railway conditions, that number typically ranges between 0.35 and 0.5. That moderate friction level creates enough grip for traction while keeping rolling resistance remarkably low once motion begins. Low rolling resistance is the first key to the puzzle. When a heavy object slides across a broad surface, friction rises dramatically because more material is in contact. Railroads minimize that contact. Smooth steel wheels meet smooth steel rails with a very small interface, which means once the train starts moving, it requires surprisingly little force to keep rolling. The resistance of a moving freight train on level track can drop to only a few pounds of force per ton. That efficiency explains how trains glide for miles with steady momentum, conserving energy in ways rubber-tired vehicles never could. The physics alone, however, does not explain how the locomotive avoids wheel slip while starting such massive loads. Adhesion comes from weight pressing those small contact patches into the rail. A standard 6-axle freight locomotive weighs around 368,000 pounds, distributed across 12 driving wheels, arranged in 2 6-wheel trucks. Dividing that weight evenly places roughly 30,000 pounds on each wheel. That downward force creates the normal force required for traction, and when multiplied by the coefficient of friction, it determins the maximum tractive effort available. A 100-ton locomotive under good conditions can generate approximately 350 kilonewtons of tractive effort, which converts to about 78,000 pounds of pulling force. That force is what allows the locomotive to begin overcoming resistance without spinning uselessly. Railroads also anticipate adverse conditions. Rain reduces adhesion. Ice transforms rails into polished ribbons. In autumn, crushed leaves can form a slick, hardened layer that significantly lowers traction. To counter this, locomotives carry sanders, small hoppers that release sand directly in front of the drive wheels when activated. The sand increases friction instantly, restoring grip and preventing wheel slip. Even so, most of the time the locomotive's mass alone provides sufficient adhesion to perform its work without assistance. Modern traction systems further amplify that capability. Older locomotives relied on DC traction motors, which converted roughly 70% of engine output into usable pulling power at the rail. Contemporary AC traction systems improve that efficiency to around 80%. That 10% gain may sound modest, yet in freight railroading, it translates to thousands of additional tons moved over long distances. AC traction motors also deliver superior low-speed torque control, reducing wheel slip during heavy starts and maximizing adhesion under load. As a result, a modern AC locomotive can often replace 3 to 5 older DC units while performing the same task. Still, the greatest challenge occurs at the moment of starting. When a train is stationary, static friction holds every wheel of every car in place. Overcoming static friction demands more force than maintaining motion once rolling. On level track, moving a freight train requires roughly 2 to 5 pounds of force per ton to overcome resistance, depending on speed and conditions. For a 10,000-ton train, that translates to 20,000 to 50,000 pounds of force simply to break free from rest. If the locomotive attempted to move the entire consist simultaneously, it would exceed its available adhesion, and the drive wheels would slip before the train budged an inch. The solution lies in a component hidden in plain sight behind every coupler on every railcar: the draft gear. While many recognize the loud metallic clanking that echoes through a train yard, few understand the mechanical sophistication responsible for that sound. Draft gears act as massive shock absorbers housed within the coupler assembly. They allow several inches of longitudinal travel as the coupler slides in and out within a sleeve. That travel permits what railroaders call slack action, and slack action changes everything about how a train begins to move. When the locomotive eases forward, it does not engage the full weight of the train at once. It first tightens the slack between itself and the first car. The draft gear compresses, the first car overcomes static friction, and it begins rolling. Only then does the coupler between the first and second car extend, transferring force rearward. The second car breaks free, followed by the third, then the fourth, continuing sequentially down the length of the train. This progression can travel for a mile or more on long consists. During that time, the locomotive at the head end might already be traveling at several miles per hour. The last car remains stationary, waiting for the pull to reach it. That staggered engagement prevents the locomotive from facing the entire static resistance simultaneously. Instead of battling 10,000 tons at once, it tackles one car at a time, incrementally building motion throughout the consist. Without draft gears, starting heavy freight trains would require several locomotives coupled directly and applying enormous simultaneous force, increasing both mechanical stress and fuel consumption. The draft gear system transforms a potentially overwhelming force requirement into manageable steps, preserving traction and protecting equipment. Historical evolution deepens appreciation for this system. Early railroads used journal bearings that created significantly more rolling resistance than today's roller bearings. Engineers had to manage throttle settings with extreme care to avoid slipping wheels while coaxing heavy trains into motion. The introduction of roller bearings dramatically reduced friction, improved reliability, and allowed longer trains with fewer locomotives. Combined with advancements in metallurgy, traction control electronics, and distributed power systems, freight railroading evolved into one of the most efficient, large-scale transportation methods ever developed. Efficiency statistics reinforce that reality. Rail transport in the United States can move 1 ton of freight more than 470 miles on a single gallon of diesel fuel under favorable conditions. That remarkable figure stems directly from the physics of low rolling resistance and steel-on-steel contact. Highways cannot match that efficiency because rubber tires deform, creating energy loss with every rotation. Trains avoid that penalty, allowing a single locomotive to haul thousands of tons across flat terrain with consistency and control. All these elements converge into a coordinated system. Low rolling resistance keeps momentum alive once movement begins. Concentrated locomotive weight provides adhesion through those small contact patches. Advanced traction motors convert diesel power into usable torque with impressive efficiency. Draft gears distribute force gradually along the train, overcoming static friction in sequence rather than in a single overwhelming surge. Together, these factors allow one locomotive to move between 10,000 and 12,000 tons across level track, accomplishing work that once required multiple engines. The spectacle becomes more meaningful when viewed with this understanding. A freight train passing a crossing is no longer a random procession of cars, but a moving demonstration of applied physics refined over more than a century. Each wheel rests on a contact patch no larger than a coin. Each coupler hides a shock-absorbing mechanism that makes incremental motion possible. Each traction motor channels controlled power into steel wheels gripping steel rails. The system appears simple from a distance, yet beneath that simplicity lies deliberate engineering precision. Freight railroads have been refining these principles for over 150 years, steadily increasing tonnage, improving fuel efficiency, and strengthening components while respecting the same fundamental laws of physics that governed the earliest steam locomotives. The massive trains rolling across North America today represent the culmination of incremental improvements layered upon foundational ideas about friction, mass, and mechanical advantage. What looks effortless is in fact the result of disciplined engineering, careful design, and relentless optimization. The next time a freight train rolls past, stretching far beyond the horizon with car after car following obediently behind a single locomotive, the numbers will carry greater weight. How does one machine manage to pull 50 times its own weight, turning physics, engineering, and mechanical ingenuity into something that seems effortless? What do those tiny contact points, massive steel wheels, and carefully calibrated draft gears reveal about human innovation? Could modern locomotives handle even more if designs continue to evolve, or are there limits yet to be tested? How much do traction systems, AC motors, and sanders contribute when conditions are less than ideal? And when watching trains in your own town or passing through rural stretches, do you ever stop to think about the immense coordination and planning behind each journey? Tell us down below. Hit subscribe and turn on notifications to catch deep dives into engineering marvels, mechanical design secrets, and the incredible physics behind the machines shaping our world.